Now, you guys used this equation last time in the drill to calculate the radius. So the radius is the distance from here to here. And we're just going to calculate it by using the mass of the proton times the velocity, and then you divide that by Q times the strength of the magnetic field. And then we can also calculate this quantity that is called the orbital period. So this is just the time that it takes to make one complete oscillation. So for example, the time that it takes to start from point A and then go back from point A to point A, right? So this time is the time that is going to take to do one revolution, right? And in one revolution, the distance that you travel is just given by the circumference, which is 2 pi times the radius. And then you divide that by the magnitude of the velocity, you should get the period. Okay. Now, what you see on so we're not really going to use this, but what this tells me is that, so in this example here, the velocity, so velocity is at 90 degrees with respect to the magnetic field. So when the velocity makes 90 degrees to the magnetic field, then the particle is going to move in a circle. But if the velocity is not at 90 degrees to the magnetic field, then it moves in a helical. This is called a helical path. Now, a helix is a circle that is changing with time. It's an oscillating circle. So instead of the electron, the proton just moving on a circle, right? It's moving on a circle, but at the same time, it's also moving along the x direction. So when you look at that, it's going to show up as an oscillating circle. So it's going to create that helical path. But I think for purposes of applications, we're just mostly going to focus on this, on the circular motion. Okay, so this is one example here. And I'll just go over this real quick because I think you guys saw something like this in the drill. So this is example number 28.2. So in example number 28.2, what we're interested in calculating is, so we say that suppose that you have a proton that is moving in a circular orbit and the radius is given as 14 centimeters. Then it tells me what the strength of the magnetic field is. And in this example, we know that the magnetic field makes 90 degrees with the velocity of the proton. So once this makes 90 degrees, we know that this is going to move in a circular. So this is going to be in a circular path. So I can go ahead and use this equation here to calculate the velocity. So this equation comes from, again, remember that R was equals to mv over 2b. So if you rearrange this equation, you get this equation right here. Because if I know mass, velocity, charge, and the strength of magnetic field, I can calculate radius. But in this problem, it gives me the charge, it tells me what the strength of the magnetic field is, and it also gives me the radius, and then it's asking me to find the velocity. So I can rearrange this equation here. So take this equation and just rearrange it, you get this, and then if you plug in the values, you should calculate this as the speed of the program. Now it says that what if an electron instead of a proton moves in a direction perpendicular to the same magnetic field? So the same magnetic field means that the strength of the magnetic field is equal to 0.35 Teslas. All right, and then with the same speed. So again, you can say that the speed right here is the 4.7 times 10 raised to the power of 6 meters per second. And so I want to calculate the radius. So if you calculate the radius, you just use this equation here. we go back and use this equation. So R is equals to M. So remember that for a proton, the radius was equals to 14 centimeters. So we saw that for a proton, the radius was 14 centimeters. This was for the proton. Now, if I use this equation for an electron, all what changes is the mass of an electron. So you want to substitute 9.11 times 10 to the negative 31. Then you multiply that by the velocity, which is 4.7 times 10 to the power 6. So the charge is the same, 1.6 times 10 to the negative 19. Then you multiply that by 0.35. So you can calculate this. So let's call this the radius of the electron, and then this will be the radius of the proton. So if you do this calculation here, then you can compare, you want to compare this value to that value right there. All right. So for the sake of time, I'm not going to do that calculation, but you guys can plug in those numbers and try to see is it going to be greater than 14 centimeters or less than 14 centimeters? Okay. All right, so let's look at this second example here. And this is example number 28.3. So if we go ahead and just try to see what the problem is talking about, it says that in an experiment where we're trying to measure the magnitude of the uniform, so we'll try to calculate the P field, and it says that electrons are accelerated from rest with a potential difference of 350 volts, and then this is going to enter a region that has a uniform magnetic field that is perpendicular to the velocity vector of the electrons. And the electrons are going to move in a curve with this radius here. Now, what is the magnitude of the magnetic field? Now, let's just see what we need to calculate here. So you can see in this picture here, this is the electrons that are moving like that. And it tells me what the radius is. So and remember that, so if you go back to this equation here, so R is equals to M times V divided by Q times B. Now, if you look at that equation, what are we trying to calculate? We're trying to calculate B. So if we're trying to calculate B, it means that I can rearrange this equation and write this equation as B. So from this equation here, you can write this as B is equals to M times V divided by Q times R. So let's see, do we know what the radius is? The radius is 7.5 centimeters. Do we know what the mass of an electron is? It's 9.11 times 10 to the negative 31. Do we know what the charge of an electron is? We know that this is just 1.6 times 10 to the negative 17. So how do we get the V, the velocity of the electron? So we just need to calculate the velocity of the electron. And it says that the electrons are accelerated through a potential difference of 350 volts. So if you remember what we said, we take Q times delta P. So Q times delta P gives me, it's an energy, and this energy, you can write that as 1/2 mv squared. So assuming that V initial is equal to 0, so if the electron starts at rest, I can just say that Q times delta V is equal to 1/2 mv squared. So I can solve that equation there to get my velocity. So let me share let me stop sharing here. I want to share this other screen very quick here. Just because I want to explain the physics of the problem a little bit more. So this is the problem right here. So again, we take very, very low energy electrons, which we can assume that the V initial is equal to 0. And then you want to accelerate those electrons through, in this case, let me put this in this. So let's say that we want to accelerate it in such a way that so the electron is coming in here with a very small velocity that we can say V initial is just 0. Then this is plus. Now the electric field is pointing like that. The potential between these 2 points is 350 volts. So the exit velocity is V, is what I want to calculate. Now, do you see that the reason why the electric field is pointing to the left is because I want to accelerate the electrons in what direction? To the right. And we know that an electron carries a negative charge. So it means that if I want to accelerate the electrons to the right, I must put an electric field that is pointing to the left. Then if you go back in chapter number, I think 22 or 23, force is equals to Q times E. So for an electron, because Q is negative, I need to make the electric field to be pointing in the negative I direction to get the force on the electron to be pointing to the right. Okay. So now these electrons coming out here are going to go through this region that has a magnetic field. This will move in a circular path like that. And I know that the radius is given by, let's say, 7.5 centimeters. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. We can write this as 7.5 times 10 to the negative 2 meters. Mass of an electron is 9.11 times 10 to the negative 31 kilograms. So we know that R is equals to M times V over Q times E. So I want to calculate the strength of the magnetic field. I can rewrite this equation as M times V divided by Q times R. So what we need is that we need this entrance velocity V, which I can calculate this entrance velocity by saying that the charge of an electron times the potential difference is just going to show up as an increase in the kinetic energy. Now we can take this V initial as 0 because we assume that the initial velocity is a very, very low, it's a low velocity. So we don't really care about the initial value. And so solving this equation, I can get my V. So my V is equal to 2 times Q. Then divide by mass. All right, so this is V. So to calculate V, we need V, which is Q, 2Q. So this is 2Q. Where delta V is equals to 350. All right, so first, you do this calculation for V. Then once you get V, you can plug it into that equation to get the strength of V. Okay, so let's go back and look at the answer. So let me stop sharing here. Share this screen. So let's look at the answer right here. If you do the math, first you want to calculate that velocity here. That velocity should come out to be about 1.11 times 10 to the power 7. Then using this equation here, you can calculate your B field. And if you just substitute the values, you should get the B value of about 8.4 times 10 to the negative 4.